Hi guys, and welcome to the first activity in Physical Sciences for Year 9. In this activity we're going to explore the concepts of heat, temperature and how heat moves from one object to the other. Okay, so the first thing that we need to understand is that heat energy is basically how hot an object is. It's the amount of energy that a substance holds within its molecules. Now remember, molecules and particles have vibrational energy. Now the hotter an object is, the more vibrational energy they have, from a solid all the way through to a gas. So if you've got a really hot object, it means it's got a lot of energy. A cold object basically has only little energy. Now there is no such thing as cold. All it means is there is an absence of heat energy. Now heat energy is measured in joules, and what we find is that heat energy will move from an area where there's lots of heat energy, i.e. a hot object, to areas where there is very little heat energy, a cold object, so it moves from hot to cold. Now this shouldn't be confused with the concept of temperature. Temperature is just basically a numerical value which indicates how much heat energy is present in an object. Now if you remember back to the Year 8 course, we did a unit where we looked at the heat energy in food, and we used an equation where we had volume of water multiplied by 4.2 times the temperature difference will give you the amount of energy which is necessary to raise the temperature of some water a certain number of degrees. So what I'm trying to get over is the fact that although you may have a temperature of a certain value, that doesn't relate to the numerical value of the heat energy. The heat energy is going to be a lot bigger. Okay, so when we look at temperature, we're just looking at an indication as to how much heat energy may be present in that object, but it doesn't give us the numerical value of how much heat energy there are in joules. Now, temperature, there are lots of different temperature scales. We've got three main temperature scales that we look at. First one was devised by Daniel Fahrenheit. A picture of him is here. Now, Fahrenheit tends to be used a lot in America, whereas here in Australia, we basically use the second type of temperature scale, which is Celsius. There is one other temperature scale, which we'll talk about in a second. Now, Celsius basically worked on the concept that he looked at the concept of water. So he looked at temperature and looked at heat energy, and water freezes at 0 degrees C. It boils at 100 degrees C. As a result, he set up a decimalized temperature scale going from 0 to 100, and anywhere in between obviously was scaled up. So Celsius looked at that sort of temperature scale. Now Fahrenheit is totally different. There is one other temperature scale which is devised by Lord Kelvin, who is a British scientist, and basically we call this the absolute temperature scale. Now the absolute temperature scale basically puts 0 as the coldest object that we can find on this planet. Now most of the time that is way down and is done in the lab, and the value at 0 degrees Celsius, the Lord Kelvin basically, at 0 degrees Kelvin, Lord Kelvin basically found out that this was minus 273 degrees Celsius. Okay, so why it's an absolute is because, as far as we know, man can't get any colder than minus 273 degrees Celsius. But obviously, Andre Celsius didn't realize or couldn't demonstrate that in the laboratory. He only had water to deal with. So as a result, Lord Kelvin made 0 that minus 273. That's why it's absolute, and then he used going up in tens all the way through. So when we get to 0 degrees Celsius, it would be 273, 0 degrees Celsius would be 273 degrees Kelvin. So I hope that gives you a rough indication with respect to temperature. Obviously temperature will will be measured with a thermometer, and it just looks at the expansion of a liquid within the tube, and as a result a scale can be added. So the hotter an object is, the more heat goes into the liquid, it expands up the tube, and then you can read off the scale. So basically what we've got to understand is temperature is just an indication of the amount of heat energy which is present inside an object. Okay, so let's look at how heat energy moves. Well, it's very, very simple to follow. In nature, everything wants to be equal. It doesn't like it where you've got a large amount on one side and only a small amount on the other. So it's always going to try and move from one to the other until both sides are equal. Now, obviously, it will have to move through a material. Now, that material could be solid, could be a liquid, it could be a gas. And the degree or ease with which it can move obviously will vary from one material to the other depending on how the particles are set up. The key to understand is that it will always move from an area where you've got a hot object, i.e. a lot of energy, to an area where you've got a cold object, very little energy, until the two are equal. Now those two energies will be the same, and eventually their two temperatures will end up being the same. Well, let's take an example like we've got here. We've got a bathtub at 45 degrees and a human being sitting at 37 degrees. Note this is in Celsius. Now what we'll find is that the heat from the bathtub will move into the body. That's why if you jump into a bathtub, your skin goes red. Why is that? Because it's getting a lot hotter, so the blood comes to the surface to try and remove all that heat so you don't overheat. So the heat energy will move from the bathtub into a colder body. However, let's say you've got a high fever and we want to bring down your fever, then what they will do is put you in a cold bathtub. So you see we've got a cold bathtub here at 4 degrees and we've got a body at 37 degrees. Now obviously the body is hotter than the bathtub, so the heat will go from the body into the bathtub. So the heat will move out, which will cool you down. So again, we get this situation where we're moving from an area of hot energy, lots of energy, to an area where there is very little energy. We call that cold. Another example is shown here in this diagram. If you look at the top situation, we've got a hot object. Now you can see that that hot object has caused the thermometer to rise, so we would call that a high temperature. And what will happen is that the heat will move from that hot object through into the cold object, the area denoted by blue. And we can see that the thermometer there is very, very low. That will continue to happen until both sides are equal, that both sides will have the same amount of heat energy. If they both have the same amount of heat energy, they will both have the same thermometer. Just note that the amount of heat energy will be different to the numerical value of the thermometer. Okay, so if you had 300 joules of energy, it doesn't mean you've got 300 degrees C. Okay, so let's just summarize. Heat will always move from areas where we've got a lot of it, i.e. a hot object, to areas where we've got little heat energy, i.e. a cold object, until the two energies are the same or the temperatures of both objects are the same. Okay, so let's try some exercises, and I'll run through some examples and then you can do some exercises for yourself. So in this case, the sort of question that we might get, we've got two objects. We've got a metal object at 300 joules here on the left hand side, and we've got air at 100 joules of energy. Now it says using an arrow, show how much, show the direction that the energy is going to move. Well, the energy is going to move from areas where we've got lots of energy, i.e. in the metal, to areas where we've got only a little amount of energy, such as in the air. So the arrow is going to move from left to right. So it then asks, look at how much the energy is decreased. Now remember what we said. Energy will move from areas where we've got lots of it to areas where we've got little until they're both the same. So the mechanism to work out how much energy there is or how much it's decreased can be found here. Firstly, let's find the energy difference. Now the energy difference in this case will be 300 minus 100, okay, which leaves us 200 joules energy difference. Now if we divide that by 2, what that will mean is we will have equal numbers of energy on one side as we've got as the other. So if we divide 200 by 2, we end up that the metal will decrease by 100 joules. Now if you think about that, the metal will decrease by 100 joules and the air will increase by 100 joules. So let's take 100 joules away from the metal. That leaves us 200 joules left over. Let's look at air gaining 100 joules. That will also gain 200 joules. So we'll have 200 joules on the left, 200 joules on the right. Everything is equal. So our law has been obeyed. So Once you've found your temperature difference, divide it by 2 and that will tell you the energy decrease. That's how much the energy has been lost from the metal. Okay? As a result, you can also say how much the energy will increase on the air side. You'll also be able to then work out how much energy is left, or what both sides will equal in the end. So let's look at an example where we have to do that. So in this case, what I've done is use the idea of temperature. Okay, you can see that both the metal and the air have got degree C written after it. Now in this case, we've been asked to work out which direction is the energy going to move and what will the final temperature be when it's completely moved, once equilibrium has been reached. So obviously it's going to move from an area where we've got high temperature to low temperature, large amount of energy, small amount of energy, so it's going to move left to right. Then we follow our rule. So the first thing we need to do is to find the energy difference, which is 200 degrees Celsius. Divide that by 2, so that now we've got equal sharing between the two scenarios. So we've got 100 degrees C is going to move from one place to the next. So then what I'm going to do is I'm going to take 100 degrees C away from the metal, and that leaves me 200 degrees C, which means that the metal and the air, when they reach equilibrium, if it's all enclosed and it can't get out anywhere else, will be 200 degrees C between the two. That is the point of equilibrium. I could also add the 100 to the air, which would also equal 200 degrees C, depending on how the question is written. So, the exercises that we've got in Activity 1B will allow you to do this sort of calculation. So I hope that you found that useful, and I hope you understand the difference between heat energy, temperature, and how heat energy moves from one place to the next. Okay, join me again, and thanks for watching.